We've been talking so far about basically overviews of supply and demand relationships and understanding how markets work. Now we're going to sort of go step back and get behind the supply and demand curves, okay, and understand where those curves themselves come from. So we talked about, given that we have supply and demand curves, how they interact. Now we're going to get behind that and say, where do these curves actually come from? Thank you, by the way, for coming down. I appreciate it. Okay, so what we're going to do is we're going to start with the demand curve, and we'll spend the next few lectures talking about consumers and how consumer preferences are ultimately what leads to the construction of the demand curve. Then after that, and after the midterm, after the first exam, that'll cover what's on the first exam. After the first exam, we'll start talking about firms and what determines the firm supply curve. So today we'll talk about consumers, and we're going to talk about where the demand curve comes from. And where it comes from, and where all consumer behavior comes from in economics, is from utility maximization. That's where everything with consumers starts with utility maximization. That's the basic building block of consumer behavior. Okay? And basically, the utility maximization, and this is what this lecture will be about describing it. But basically, an overview is we posit some type of preferences. We posit consumer preferences, what consumers would like. We posit some budget constraint, what resources consumers have to get what they'd like. And then we do a constrained maximization problem that says, given your preferences, given what you'd like, subject to the resources you have available, what choices will you make? Okay? And in particular, we're going to ask, the term we'll use will ask, what bundle of goods makes you the best off? Given your preference, given your constraint, what bundle of goods? So think about consumers choosing across a set of goods. Typically, we're going to think about two goods, because graphs are easier to think about in two dimensions than more. Okay? So we'll typically think about trading off two goods. So think about consumers with preferences across two goods, some budget they can allocate, and how that they make those choices. But this basic framework applies to the multiplicity of choices we all make along many, many dimensions. So doing two dimensions to make as one of the simplifying assumptions I'll talk about. But that's just a simplifying assumption. So basically what we're going to do is we're going to go through this in 3 steps. Okay, not just in this lecture, but over the next few lectures. Okay, step 1 is we're going to talk about what assumptions we make about preferences. So we'll talk today about preference assumptions. So sort of the axioms that underlie how economists model consumer preferences. We'll then talk about how we translate these preferences assumptions into mathematical tractability through the use of the utility function, which is basically a mathematical representation of underlying consumer preferences. So we'll talk about how we basically take these preferences and translate them to something that we can work with here at MIT by making it mathematical, by making a utility function. And then finally, we'll talk about budget constraints. And armed with these 3 things, we'll then be able to model how consumers make decisions. Now, importantly, for today's lecture, we are not dealing with budget constraints. So this is not happening today. So today we're not going to worry about the budget constraint. Today we're in a world where we're just going to talk about what people want, and we're going to put out of our mind whether or not they can afford it. Okay? So just talk about what people want. We'll put it out of the mind for today. We'll come back next time to whether they can afford it. Okay, we're just going to think about unconstrained preferences today. Okay, for today's lecture. Now, so let's talk about our preference assumptions. So to model consumer preferences, consumers' preferences across goods, we're going to impose 3 preference assumptions. Three preference assumptions. Assumption 1. Now, once again, let me remind you from the first lecture. This is getting to some of the harder material. I'm going to write messily and talk quickly, so stop me if anything is unclear. And if you don't stop me, I'm just going to go faster and faster until I explode. So basically, feel free to interrupt and start with questions and such. OK, 3 assumptions on preferences. The first assumption is completeness. The first assumption is the assumption of completeness. When comparing 2 bundles of goods, you prefer one or the other, but you don't value them equally. Okay, when comparing 2 bundles of goods, you prefer one or you prefer the other, but you're not indifferent. Completeness is the same as no indifference. So what we're saying is whenever I offer you 2 bundles of goods, you can always tell me which you like better. Now, it could be infinitesimally better. I'm not saying you have to have strong preferences, but you cannot say I'm indifferent. You can never be purely indifferent. There always has to be some slight preference for one bundle of goods over another. That's the completeness assumption. Okay? This is an assumption we make. Now, in reality, oftentimes we are indifferent. But once again, this is one of these simplifying assumptions that will make the model work. And in fact, in reality, if forced, you can always decide whether you like one thing better or another. We just often sort of follow heuristic rules where we say we're roughly indifferent. We're just going to say more precisely, you're never purely indifferent. Okay? So I'm not sure is not an option. Okay? You can never say, I don't know which I prefer, I'm indifferent. You can't. I'm sorry, let me back up. I'm using the wrong word. I want to forget I said indifferent because we want to use that word in different contexts later. You can't say, I'm not sure. You can't say, I'm not sure. You can't say, I'm not sure. You can't say, I don't know how I feel about that. Completeness means that, yeah, I'm sorry, I messed this up. So just scratch what I said a few minutes ago because I want to use indifference differently. Completeness is not about not being indifferent. We're going to use that. What I'm saying is about not being sure. You've got to value every bundle of goods you've got to be willing to value every bundle of goods that's given you. Okay? So you can't say, I don't know how I feel about that. You've got to have some feeling about stuff. You can't say, I'm not sure. You've got to have a complete set of preferences over all bundles of goods that are given you. Okay? That's completeness. The second is transitivity, which is something we've been learning since kindergarten about transitivity, right? In all sorts of different contexts. That's just for X to Y and Y to Z, you got to prefer X to Z. Okay, you guys should do transitivity in your sleep by now. Okay, so the standard transitivity we always assume in math class, we're going to assume here as well. Okay, that should be pretty non-controversial. Okay, and then finally, and probably most controversial, is we're going to assume non-satiation. Or the famous economic assumption of more is always better. Okay? More is always better. That is, you never would turn down having more. Now, we're going to talk later today and tomorrow about why you might not like the next unit as much as you like the current unit. But you'll always like it greater than 0. You're always happy to have more. You never say, I've had enough. I literally value at 0 the next unit. You may value it as epsilon, but you always value it as greater than 0. That's the non-satiation assumption. More is always better. Now, this is the most controversial. Obviously, we can think of many contexts in which that's not true. But that makes if we don't allow for the assumption, the modeling gets a lot trickier. So once again, let's put it out of our mind. Realistically, we know once we've eaten a certain amount, literally it'd be negative. We literally do not want any more. Okay? So we're going to put that aside. Assume we're always in a space where we can always eat a little bit more. Okay? We'll call it like the Jewish mother space. Okay? You can always eat a little bit more. Okay? You can always eat a little bit more. We're just going to assume we're in that space for now. Okay? And so for large ranges, we can see it's not an unreasonable assumption, although at the extremes you can see this becomes unreasonable. Okay, so those are assumptions. Completeness, which once again I screwed up in describing. Come back to the second way I described it, which means you can't say you're not sure. You always have preferences over things. That doesn't seem unreasonable. Transitivity, which we've been living with since we were kindergartners, and non-satiation, which could be a little more controversial, but we'll live with it for now. Now, given these, we're going to talk about the properties of what we call indifference curves. This is why I screwed up before. Of course you can be indifferent between things. That's the whole point of economics. I don't know why I got that wrong. Haven't taught this course in about 6 years, so I lost track of things. Okay, properties of indifference curves. So indifference curves are our name for what you could also think of as preference maps. In economics, we like to be able to describe everything, as I said, 3 ways: intuitively, graphically, and mathematically. Preference maps are the graphical representation of people's preferences, which we do through graphing something called indifference curves. Okay, so now let's go to the example I'm going to use, that I'm going to use throughout these next couple lectures, of a decision you have to make. Now, I tried to think of a cool way to make this example cool, and I just couldn't. So it's going to be a boring example. It's going to be, imagine your parents gave you some money, and you had to decide whether to buy pizza or see movies. Okay, I tried to make it at least a little bit relevant, even if I couldn't make it cool. Okay, you got to decide whether to buy pizza or see movies. That's your decision. That's the trade-off you're making. We're in a world where there's only two goods, pizza and movies. Okay, and you're deciding how to allocate the money your parents gave you over pizza and movies. Okay? Now let's say that we're going to consider three choices of pizza and movies. So go to figure 4.1a. Okay? We're going to consider you can have two pizzas and one movie. You can have, that's point A. You can have one pizza and two movies, that's point B. Or you can have two of both, that's point C. Okay? There's just three choices you're facing. Once again, we're ignoring paying for them. Budget constraints is next time. Now we're just saying I'm giving you these three choices. Well, how do you feel about them? Well, let's assume that you're indifferent. And this is why you can be indifferent. This is what I said before, just strike. Let's say you're indifferent between two pizzas and one movie and one pizza and two movies. Let's say you're pretty much, roughly, if you had two pizzas and one movie or one pizza and two movies, you pretty much feel the same about them. But clearly, you like two pizzas and two movies better than either of the first two combinations. Okay? Then what we can do is we can draw what we call indifference curves. And that's in figure 4.1b. These are maps of your preferences. An indifference curve is the curve showing all combinations of consumption along which an individual is indifferent. Okay, I'll say that again, very important concept. An indifference curve is a curve showing all combinations of consumption along which an individual is indifferent. So you have an indifference curve. I said you were indifferent between A and B. So you have an indifference curve that runs between A and B. That means that and I'm assuming that all combinations along this curve you're indifferent. So you're equally happy getting two pizzas in one movie or one pizza and two movies. But point C, which is two pizzas on two movies, is on a different indifference curve. You're not indifferent between point C and points A and B. Okay? You're indifferent between A and B. I'm just assuming this. I'm not saying you are, but I'm just assuming. Let's imagine you are. But you clearly like two pizzas and two movies better than one of one and two of the other. Yeah? Does that break the, why would that break the?
Do you prefer pizza over movies or movies over?
No, because this is my screw up before. Completeness just means you know how you feel about everything. So that's why strike from the record my initial description. Completeness means you just know how you feel about everything. You're allowed to be indifferent. Completeness just means you can't say, I don't know, I don't know how I feel about pizza. You got to have feelings for pizza. Okay? You got to know how you feel about stuff. That's what completeness is. Okay? So, armed with those assumptions, okay, there are four key properties of indifference curves that we have to keep track of. Four key properties of indifference curves. The first is that consumers prefer higher indifference curves. So you prefer higher indifference curves. Prefer higher indifference curves. What I mean by that is the further out is the indifference curve, the more you prefer it. And this comes naturally from the non-satiation assumption. Okay? Given that we've assumed non-satiation, you must always prefer an indifference curve that's further from the origin, because it's more, and more is better. Okay? So given non-satiation, you will always prefer indifference curves that are further from the origin. Okay? That follows directly from non-satiation. The second point is that indifference curves are always downward sloping. Indifference curves are always downward sloping. Okay? Indifference curves are always downward sloping. And that, once again, comes from non-satiation. To see this, let's look at the next figure, an upward sloping indifference curve. Why does an upward sloping indifference curve, someone tell me, violate non-satiation? Yeah?
Because you're indifferent to getting more.
Yeah, because this would say you're indifferent between 1, 1 and 2, 2. It's not quite drawn right. We ought to just have this go through to point 2, 2. But basically, this would say you're indifferent between getting 1 pizza in 1 movie or 2 pizzas in 2 movies. You can't be, because that violates more is better. So indifference curves can't be upward sloping. They've got to be downward sloping by the non-satiation assumption. Okay? That's the second property of indifference curves. Okay? The third property of indifference curves is indifference curves cannot cross. Indifference curves cannot cross. Okay. Why can't indifference curves cross? Well, here, I forgot to have Jessica do a pretty diagram, so you have to see why. You have to deal with my ugly handwriting here. So why can't indifference curves cross? Well, imagine a situation where you have your pizza and your movies, okay? And imagine a situation where you have one indifference curve that looks like this, and one indifference curve that looks like this. Okay? 2 indifference curves. And you've got, let's label these points A, B, and C. Now, could someone give me, based on the properties of indifference curves that we talked about over here, given these 3 properties, can someone tell me why this is a violation? Yeah?
Because A and B are on the same curve, meaning you're indifferent between A and B. A and C are also on the same curve because you're indifferent between the 2. But that means you're also indifferent between B and C, which can't be true because more is better.
Exactly. So transitivity says I must then be indifferent between B and C through the logic you just laid out. But I can't be indifferent between B and C because B dominates C. B has, basically the same number of movies but more pizza, so I must like B better. So by the combination of transitivity and non-satiation, indifference curves can't cross. And finally, completeness, which is the most awkward of these assumptions, it simply means you can't have more than 1 indifference curve through a point. Okay? So basically, the idea of every possible bundle has 1 indifference curve. You can't have 2 indifference curves through it saying, I'm not sure which indifference curve I'm on. I'm not sure how I feel about this. You know how you feel. There's 1 indifference curve through every bundle. Okay? There's not 2 indifference curves through a bundle. Okay? So this is the way we think about preference maps, which is the sort of core building block of utility theory. Now, I was undergrad here, took this course, but I never really understood indifference curves until I had a year up with a grad student who was trying to decide where to take a job. And he did it through just showing me an indifference map. He said, look, I'm trying to decide where to take a job, and I care about 2 things. I care about how good the place is and where it is. Okay? So he said here he had location, and he had sort of academic rank. And he said, look, I'm indifferent between Princeton, which has a shitty location, okay, but a wonderful academic rank. Okay, I'm from New Jersey, but it's still a shitty location. Okay, and Santa Cruz. Okay, and Santa Cruz, which has not such a good academic reputation, but a pretty awesome location. And he said, here's my indifference map. Okay? And where did he end up going? He ended up going to the IMF, the International Monetary Fund in DC, which had a better location than Princeton. Okay, better location than Princeton, worse than Santa Cruz, but a better reputation than Santa Cruz and worse than Princeton. So he decided he was indifferent along this map, and he ended up choosing a point in the middle. But indifference curves are just a way of representing 2-dimensional choices. Okay? Now, very few choices in life are purely 2-dimensional, but that's a nice example. Question in the back.
I was wondering if IMF, the point would be actually not on the curve, but further out?
If we're further out, the great question. So imagine the IMF were here. Okay? What should he have done? Definitely go to IMF. Here is he was indifferent. He could flip a coin and be equally happy at all 3. But if IMF were out here, and maybe it was because that's what he chose. That's a good point. I don't know if IMF was here or here. I can't. The fact he chose IMF, it can reveal it wasn't anywhere in here. This is a very good point, actually. It can reveal it wasn't anywhere in here. That we know. But I can't tell if it was on the curve or outside the curve. Could have been on the curve because he's indifferent, so who knows, could have flipped the coin. Or could have been outside the curve because it's better. We can't tell that. That's a good point. All right? So that's a preference map. That's indifference curves. OK. Now, let's step from indifference curves, which is the building block of preferences, to actually to utility. Now, everything you need to know about preferences is represented in those indifference maps. Okay? The problem is they're pretty awkward to work with when we need to actually prove theorems and solve and understand how people make decisions. That's a lot easier if we have a mathematical representation of those preference maps. And that's the utility function. So the utility function is a mathematical representation of preferences. That's all it is. You're going to be hearing this term in your nightmares for the next semester, okay? Utility functions. But remember, it's just a mathematical representation of people's underlying preferences. Don't be scared of it, okay? And the key thing is that we assume individuals have these well-defined utility functions. And by maximizing those utility functions, we can tell what choices they're going to make. So for example, suppose that I said that your utility function over pizza and movies was the square root of pizza times movies. That's your utility function. I say, what the hell does that mean? Well, it doesn't mean anything. It's a utility function. It's your preferences. It's a mathematical representation of your preferences. OK, what does that mean? What it means is it doesn't mean anything inherently, but it tells us about your preferences. What it tells us is that your preferences can be represented, if you flip back to figure 4.1b, okay, it tells us those are your preferences. Because you're indifferent between 2 pizzas and 1 movie, and 1 pizza and 2 movies. Of course you're indifferent. They both give you utility square root 2. But you prefer 2 pizzas and 2 movies because that gives you utility of 2. So this is a mathematical representation consistent with those utility indifference curves. Not the only one. There's other mathematical representations that could be consistent with those indifference curves. But let's posit that this is your utility function. This is the mathematical representation of your tastes. Okay? Now, what does utility mean? Utility means nothing. Okay? In the sense that it is not a cardinal concept. It's only an ordinal concept. So if I say to you that you get 2 utils from 2 pizzas and 2 movies, that doesn't mean anything. It just means that you get more than from 1 pizza and 1 movie. And we can even get the ratio that you get square root of 2 more, okay, than you get from 1 pizza and 2 movies. Okay, we can do ranking and ordinality, but we can't assign cardinality. I can't say how happy you are in some abstract, absolute sense from 2 pizzas and 1 movie. I can't give a cardinal form of preferences. But this is an ordinal ranking of preferences. I can tell what you like better than what else. So that's why utility functions are just representations of indifference maps. They're just a mathematical tool for comparing bundles. They're not some inner answer to the value of your soul or something like that. Okay, so once again, don't imbue these with too much magic. They're just mathematical ways of representing preferences. Now, the key concept, the single most important concept for consumer theory, for understanding how consumers make decisions, is the concept of marginal utility. We'll talk a lot this semester about marginal this and marginal that. Okay, and this is our first example. Marginal utility. Okay? That is how your utility changes with each additional unit of the good, or the derivative of your utility function. Okay, if you want to do it in calculus terms, marginal utility is the derivative of your utility function with respect to one of the inputs. But if you don't want to put it in calculus terms, it's as you add each unit of one of the elements of utility function, how does utility change? Okay? So to see this, let's do an example of marginal utility. Imagine for a moment that you have 2 pizzas. P equals 2. You got 2 pizzas, they're there. Your roommate's got them or something. Okay? Now I want to ask, how does your utility change as you see additional movies? And to show that, let's look at figure 4.3, which isn't here. Whoops. There's no figure 4.3. Do you guys have figure 4.3? There was never any figure 4.3. OK, great. So let's go to 4.5. OK? So basically, no, but let's just yeah, actually fine, 4.4. So basically what this is showing, what figure 4.4 is showing, is it's showing how, no, actually, no, look, let's go to 4.5. They're out of order. Let's go to 4.5. What 4.5 is showing, no, that's not going to work. OK, back to 4.4. All right. What figure 4.4 is showing is it's showing how your margin utility for movies evolves, how your utility evolves as you get more movies. Okay. Given that you have 2 pizzas, this is the evolution of your utility as you get more movies. So each additional movie increases your utility. Okay, the slope is positive. By more is better, we know that. Okay, it doesn't, even if it's, you know, even if it's like some date movie, still improves your utility. Okay? So it still improves your utility. Okay, but at a diminishing rate, and that's the key, is that we assume diminishing margin utility. The key assumption that underlies everything we'll do for consumers is diminishing margin utility. Okay? We assume that each additional movie increases your utility, but at an ever-diminishing rate. Okay? So basically, you get, so we can actually graph your margin utility. That's what figure 4.5 is a graph of your marginal utility. So in other words, when you're at, so basically when you are getting, when you have 2 pizzas and 1 movie, your utility is square root of 2, right? Now what I'm saying is if you get 1 more movie, your utility is going to rise from square root of 2 to 2. So the marginal utility of that next movie, is that right? 2 movies, 1.4. Yeah, it's going to rise by the square root of 2. You're going to multiply your utility by the square root of 2. So your marginal utility, you're going to go from utility of square root of 2 to utility of 2. So utility is going to increase by the square root of 2. Okay? Utility is going to increase. I'm doing this wrong. Hold on. 1 second. From 1 movie. I see. So I'm sorry, this isn't the delta. This is the level of margin utility. So I'm graphing the actual level of margin utility. Back up. Okay. So I'm graphing the actual level of margin utility. So when you have 2 movies, 2 pizzas and 1 movie, your marginal utility, your actual utility, I see, that's what this is. This is the actual utility I'm graphing. So I told you a minute ago we can't measure utility as a cardinal concept, but actually here I'm doing it anyway, because to illustrate margin utility. So your utility, okay, when you have 1 movie is 1.4, square root of 2. Okay, that's your utility. Now, when you move from 1 movie to a second movie, your utility goes up from square root of 2 to 2. Utility goes up by 0.6. So the margin utility of that second movie is 0.6. Utility was 1.4, was the square root of 2. Now it's increased to 2. So the margin utility of the first movie is 0.6. Now let's say you add another movie. You go to 3 movies. Well, what's your utility now? It's the square root of 6. So it's gone from 4 to the square root of 6, which is 2.45. So your marginal utility of the third movie is 0.45. Okay, so this graph is messed up because the first one is an actual utility level, and then so the first one I say for 1 movie you have a utility of 1.4. And then I'm giving, for the second movie, I give the margin utility, third movie margin utility. So this graph sort of, yeah. Yeah, but the yeah, I guess that's right, because you're 0 movies. Okay, right, you're right. Okay, so the first one's the margin utility of the very first movie, you're right. So the very first movie gives you margin utility of 1.4 because you go from 0 to square root of 2. That's right, my bad. Okay, so you go from 0 to square root of 2, so you get a margin utility of 1.4 for the first movie. From square root of 2 to 2, you get 0.6 for the next movie. From 2 to square root of 6, you get 0.45 for the third movie. From square root of 6 to square root of 8, so you only get 0.38 from the fourth movie, and so on. So the key point is that these margin utilities are ever decreasing. Each additional movie gives you less incremental utility. And if you stop and think about it, it's kind of intuitive. Just stop and think. Think about the movies you want to see right now. Okay? The 4 movies you want to see. Presumably, whichever you ranked first would give you more utility to see than whichever you ranked second. And if you think movies out right now are pretty crappy like I do, by the time you get to the 4th movie, you're not getting that much utility from it at all. Okay? Thinking about movies that are out now, you're getting a lot of utility from that first movie you see. Extra utility from that first movie you see. but each additional one's giving you less and less. And that's the idea of diminishing marginal utility. Likewise with pizzas, if you haven't eaten all day, that first pizza can give you a very high marginal utility. The enjoyment you get from eating that first pizza can be very large. Okay? But the second pizza, not so much. You're already pretty full. Third pizza, even less. And then fourth pizza would probably violate non-satiation. Okay? So that's the basic idea. Yeah?
I have a question. Do we assume that the goods are homogeneous, as in, is it the same movie watched 4 times, or different movies?
Actually, that's a great question, and you have to specify that as part of the problem. I haven't specified that here. So I could, obviously it can't be the same pizza eaten 4 times. It could be the same kind of pizza eaten 4 times. But is it the same, do you see the same movie? I haven't specified that here. So there's not a general assumption about that. It depends on how I define movies. Did I define movies as, I don't know what, God, I'm terrible. All I know is the Guardians of Ga'Hoole, because I got a little kid who's interested in it, whatever movie's out. Do I find movies as Guardians of Ga'Hoole, or do I find movies as seeing a movie? And I haven't specified that. Implicit in my examples, I specified movies as seeing a movie. But you would have to specify that to be more precise if you're actually trying to figure out. It depends what you're maximizing over. Are you maximizing over seeing any movie? You're maximizing over seeing the same movie. And that I didn't specify here. It would work in both cases. Clearly, you can imagine, actually, it's a very good point. Where do you think your marginal utility would diminish more? Seeing the same movie. So what your example points out is that different goods will have different rates of diminishing marginal utility. Okay? So marginal utility will always be diminishing, but at very different rates for different goods. Okay? So the general principle is that there'll be generally diminishing marginal utility, but at different rates for different goods. Okay, so after all my mess ups, let me just review. Okay, marginal utility is diminishing because each good is worth less to you. It's always positive because of non-satiation. And this graph represents the marginal utility you get from each pizza, each movie you see, conditional on having eaten 2 pizzas. Okay, marginal utility is the increment from the next unit consumed. Okay, now let's get back on track here. Now let's go to thinking about, now that we have this concept of utility and marginal utility, let's now bring utility back to preference maps. Let's ask, given what we know about utility, what can this teach us about the shape of preference maps? What's the linkage between utility and preference maps? And that linkage comes through something we call the marginal rate of substitution. The marginal rate of substitution is the mathematical concept that links preference utility with preference maps. Okay? The marginal rate of substitution technically is the slope of the indifference curve. It's delta P over delta M. The slope of the indifference curve is the marginal rate of substitution. Okay? That's what it means graphically. Okay? But here's what you have to understand at a deeper level. What it really is, it's the rate at which you are willing to trade off. The rate at which you are willing to trade off the y-axis for the x-axis. The rate at which you're willing to trade off pizza for movies. Okay? So that's what it means intuitively. The slope of the curve tells you that you're indifferent. You remember, you're indifferent between any points along this indifference curve. You're indifferent between 1 pizza and 4 movies. I'm sorry, between 4 pizzas and 1 movie. You're indifferent between 2 pizzas and 2 movies, and 4 movies and 1 pizza. You're indifferent along all those combinations of figure 4-6. The MRS is the slope of that curve, telling you the rate at which you're willing to trade off pizza for movies. Okay, now, just a side note here, okay, you're never, of course, actually trading. There's not some market where you bring a pizza and get a movie. Okay, so when I didn't say trade, it's not like baseball cards, I said trade off. What I mean is, ultimately, you have some budget, and you have to allocate that budget. So if you decide to allocate it on pizzas, you can't allocate it on movies. Or the more you allocate on pizzas, the less you can allocate on movies. So there's always a trade-off. Remember, I said economics is always about trade-offs. Given your limited budget, there's always a trade-off. And the rate at which you're willing to trade off is your marginal rate of substitution. Given that you're going to have to trade off, and we haven't gotten a budget constraint yet. We'll get to that next time. The rate you're willing to is your marginal rate of substitution. Yeah?
Is that rate usually related to the price?
Ultimately, no, I'm sorry. The marginal rate of substitution purely comes from your preferences. Ultimately, to decide how much you actually consume, you'll need to bring in the price. So remember, I haven't talked about prices here. We haven't talked about that here. But this is a preference concept. Okay, this has nothing to do with prices. But you're getting ahead of us. We'll see next time is to decide how much you actually consume. You're going to relate the marginal rate of substitution to the prices you face in the market. And that will decide how much you consume. But this is just the utility concept. Yeah?
Did you say it was the y-axis from the x-axis? Or
Yes.
x-axis? Oh, okay. So that would be negative?
It's negative, yes,
Okay.
of course. So, right, of course, you're always happy. The point is, how many movies are you willing to give up to get another pizza? Or how many pizzas are you willing to get up? Well, actually, no, it's y to x. How many pizzas are you willing to get another movie? MRS, it's very hard to remember what's in the top, what's in the bottom. It's very careful on this. But that's why I said, remember, it's the y-axis for the x-axis. It's how many pizzas you're willing to trade off to get another movie. Okay, so, and basically, remember, when I say trade off here, this is not that you're literally trading. It's that ultimately you're going to have to make that trade-off. Ultimately, when we come to the next lecture, you're faced with a budget constraint. You're going to have to decide how do I allocate my budget across pizza and movies. The way you're going to decide that is by the relationship of how you feel about trading off one for the other. Okay? Now, here's the key feature of the MRS, which is the MRS is, yeah, question? I don't know. Yeah.
That exchange rate's always changing depending on how much you have of each, right?
Exactly. The MRS, just what I was going to say, the MRS is diminishing. Okay? Technically, when you go to grad school, you realize that margin utility isn't actually technically always diminishing. I said it is. For this course, it is. But if you want to get mathematically correct, really what's always diminishing that you prove is the marginal rate of substitution is always diminishing. Okay? So we have diminishing margin utility for the purpose of this course. But the really important concept is you have diminishing marginal rate of substitution. Okay? That the rate at which you're willing to trade off pizza for movies is going to fall as you have less pizza and more movies. Okay? So to see that, look at this graph, and let's compute the marginal rate of substitution along each segment. Okay? So let's localize. Imagine the segments were linear. Imagine we had two linear segments between these points. We don't. But imagine for a second we did. So the marginal rate of substitution from the first point, 4 pizzas in one movie, to the second point, 2 pizzas in 2 movies, the marginal rate of substitution is -2. You are willing to give up 2 pizzas to get 1 movie. Right? This is the same graph, figure 4-6. Okay, this isn't on the graph. You have to write it on. So going from that first point to that second point, you're willing to give up 2 pizzas to get 1 movie. Okay? So that rate of marginal substitution is -2. However, when you're at 2 movies and 2 pizzas, and I say, okay, how about giving up 1 more pizza to see movies? Now you say, wait a second. To give up 1 more pizza, I need to see 2 movies. My marginal rate of substitution on that second segment is -0.5. The marginal rate of substitution on the first segment is -2. The marginal rate of substitution on the second segment is -0.5. Once again, assuming they're not linear, so it's actually changing everywhere. But if they were linear, that's what it would be. Can someone tell me why? Why is the marginal rate of substitution falling? Why is the marginal rate of substitution lower on that second segment than on the first? Yeah?
Because marginal utility increases the fewer of something you have.
Exactly. So go ahead, flesh it out. Fewer something you have. So tell me in terms of the trade you're willing to make.
You value it more, so you want to trade more of something else for it.
So in other words, the point is, when I have 4 pizzas, okay, my margin of that last pizza is not very high. Okay? And I'm fine to give up 2 pizzas and plus I'm only seeing 1 movie. There's a second movie I really want to see. So you say to me, look, I got 4 pizzas, I'm seeing 1 movie. You say, hey, there's a second movie out I know you want to see. I know you don't even really value 4 pizzas, but at the end you're totally full. Would you willing to give up 2 pizzas to see the second movie? You're like, sure, why not? But once you have 2 pizzas and you've seen 2 movies, you're not that interested in the third movie, and you'll be hungry if you have less than 2 pizzas. So then you say, wait a second, if you want me to give up another pizza, you got to give me 2 movies. Okay? Because my margin utility of pizzas is rising. My margin utility of movies is falling. Okay? And that's why the marginal rate of substitution diminishes along the indifference curve. So that allows us to write mathematically the definition of the marginal rate of substitution is it's the negative of the marginal utility of movies, or more generally what's on the x-axis, over the marginal utility of pizza, or more generally what's on the y-axis. The marginal rate of substitution, first key formula you need to know for this course. The marginal rate of substitution is equal to the ratio of marginal utilities. Okay? Now, this is tricky. Okay? Once again, maybe you guys don't find it tricky. It's the kind of thing I find tricky, which is I defined it as delta p over as delta y-axis over delta x-axis. And yet, when I defined her as a marginal utilities, I flipped it. I did the marginal utility of what's on the x-axis over the marginal utility of what's on the y-axis. Why is that? Can anyone tell me why that is? Why is it flipped when I define terms of marginal utilities? Yeah?
It's a denominator, so like it is utility over like movies.
Well, look, let me try for slightly more. How does marginal utility relate? Yeah?
Marginal utility is like p over delta t, so, or delta p over p, so it gets flipped because of.
Okay, yeah, I mean you're giving the same answer, which is technically right. What I was sort of more looking for, but it's the intuitive version of that. Marginal utility is a negative function of quantity. Marginal utility is a negative function of quantity. So the fact that it's a ratio of the quantity of pizza over the quantity of movies is the same as saying it's the marginal utility of movies over the marginal utility of pizza, because marginal utility is a negative function of quantity. The more quantity you have, the lower is your marginal utility. Okay, and that's the key to understand. Okay. So it's the slope of the indifference curve, okay, which is the ratio of the marginal utilities, but it's the marginal utility of movies over pizza, okay? Because what that's saying is that as you get more movies, you care less about each additional movie, and ditto with pizzas. So basically, the key thing is, let's just look at this formula and think about it intuitively for a minute, okay? We've seen it graphically, we're seeing it mathematically. Let's make sure we understand it intuitively, okay? What this is saying is that as you get more so let's relate this to the graph, okay? As you get more movies and less pizza, as you move down that curve, more movies and less pizza, what's happening? What's happening to the marginal utility of movies as you move down that curve? What direction is it heading? What? It's decreasing, right? Because you're getting more movies, and marginal utility is a negative function of quantity. Likewise, the marginal utility of pizza is increasing because you're getting less pizza, okay? So you care about each pizza more. And that's why the marginal rate of substitution diminishes, okay? That's why it diminishes, because you move down that curve, the numerator's falling, the denominator's increasing. And that's why I have everywhere diminishing marginal rates of substitution, okay? So another way to think about this is imagine for a moment, okay, what life would be like if we didn't have diminishing marginal rates of substitution. And once again, I'm going to try, once again, Jessica, next year we'll let you make this pretty, but I'm going to try to draw it crudely here. Let's do pizzas and movies again, okay? Let's do pizzas and movies again, okay? Movies and pizza, and let's 1, 2, 3, 4. 1, 2, 3, 4. Okay? Now let's imagine that instead of diminishing marginal utility, and instead of indifference curves being convex to the origin, imagine if indifference curves were concave to the origin, which is what increasing marginal rate substitution would imply. So that'd be something where you'd be indifferent between 4 pizzas in one movie, between 3 pizzas and 2 movies, and between 1 pizza and 3 movies. So your indifference curve would look like that. Not quite to scale, but you get it. It would be concave to the origin instead of convex to the origin. In this case, marginal rates of substitution would be everywhere increasing. That is, that basically, I'd be willing to give up 1 pizza to get 1 movie. But to get that next movie, I'd give up 2 pizzas. But as you can see, that doesn't make sense. It doesn't make sense that given that as long as you're ranking your movies, or even more in the example of seeing the same movie over and over again, it's maybe more compelling, okay? That basically what you can see is that if you're willing to give the pizza to see that movie, one pizza to see that movie a second time, why would you possibly give up 2 pizzas to see it a third time? That makes no sense at all. If you like it, if you only like it so much you only give up 1 pizza to see it a second time, why would you possibly give up 2 pizzas to see it a third time? You wouldn't. Okay, it doesn't make sense. And that's why margin rate substitution has to be everywhere decreasing. It can't be increasing. Yeah?
Could it remain constant?
It could absolutely remain constant. Yes, that's right. You could be indifferent. So my indifference curves, how many of you guys seen Toy Story 3? I think it's one of my 10 favorite movies of all time, the greatest children's movie ever made. Okay, I've seen it 3 times. My indifference curve is virtually, I've enjoyed it the 3rd time as much as the 1st. It's virtually flat with respect to Toy Story 3. I could see it 10 more times, okay, and feel pretty much the same. So that's certainly possible that it would be constant, that I'd be willing to give up, whatever I pay, $10 a shot, okay, to see it. It's possible. But so basically, we will talk almost always inequalities will be greater than or equal to or less than or equal to in this course. It's more fun to talk about the not equal to case, the nonlinear case, but linear cases will exist as well. It's just it can't be opposite signed. You can't have an increasing marginal rate of substitution. Was there a question over here?
What about addictions? You can want it more the second time.
That's interesting. So how would addiction work? So basically,
I guess it is kind of, it's not really decreasing rate of return because you need more the second time, right? So it has to be.
That's very interesting. I mean, in some sense, yeah. So you give up 1 pizza for the first shot of heroin, okay, and then you're hooked. Yes. So then you'd be willing to give up 2 pizzas for the next shot of heroin. Yeah, I guess so. I guess that's right. I guess I guess we're going to have to stay away from addiction in this course. I guess for an addictive good could look like that. That's a very good point. Other questions, comments? Okay, so what we're going to do is we're going to stop here with this understanding that we're going to have, leaving this example aside, we're going to have diminishing marginal rate. Yes, one more question.
Just to follow up on the addiction, but what about in the end, if it's alcohol, doesn't the utility actually become negative because then you start feeling something like that?
I mean, basically, we're assuming by non-satiation that never happens. So once again, that would violate non-satiation. The problem with the addictiveness example is the reason it wouldn't work in this course is because eventually you'd violate your budget constraint because you'd want more and more and more. Maybe not. But in any case, we're going to ignore that example. We'll assume diminishing marginal rate of substitution. And we'll come back next time and talk about how to put this together with budget constraints to actually dictate your choices.